Today, and we have Anna Jenčová talking about Renyi relative entropies.
Thank you very much. First of all, I would like to thank the organizers for this beautiful workshop, and especially for this session dedicated to the memory of Deneš, and for letting me speak about some work which I had the opportunity to do with him, and maybe when I met Deneš, it was roughly 20 years ago, and the first problem we discussed was related to this family of Fisher informations or monotone metrics he characterized, and he was very eager to find some interpretation for these other quantities apart from the standard quantum Fisher information. And as it seems that this problem was not solved since then, and so if anybody has an idea, it would be very interesting. Okay. The topic of my talk is very closely related to the previous talks. It deals with some quantum relative entropies, especially the Renyi relative entropies, and some equality conditions in the monotonicity. So I will start with the classical Renyi relative entropies. As you know, this is a family of quantities which are parameterized by some alpha larger than 0, and if you take the limit alpha go to 1, you obtain the usual relative entropy or Kullback-Leibler divergence. So this family was introduced in an axiomatic approach by Renyi, and since then these quantities become fundamental in information theory, as you know. So what about the quantum versions? So the standard Renyi relative entropy can be written for a pair of density matrices in this way, which it seems to be a straightforward generalization of the classical quantities, but as it turned out these at least for some parameters of alpha, these are really the useful generalizations. Here you see the definition for density matrices, but actually these quantities can be defined also in von Neumann algebraic framework by using something which is called the Petz quasi-entropies. Usually introduced by Deneš in generalization of Araki's relative entropy using the relative modular operator. You have seen the definition, so I'm very happy that Professor I.I.D already introduced much of the formalism I will need. So as you already heard, Deneš worked very much in the von Neumann algebra setting, but at least in this first part I will speak about these quantities for density matrices. Now from the properties of quasi-entropies, it can be shown that if alpha is restricted to this interval, then the standard Renyi relative entropies have good properties. For example, they are strictly positive with equality if and only if those two states are equal. Then we have data processing inequality or monotonicity with respect to any quantum channel phi. Also we have joint lower semi-continuity and joint quasi-convexity in the sense that this map is jointly convex, and also some other useful properties, but still we have to restrict this parameter to this interval, and at least for alpha between 0 and 1 it is well known that these relative entropies also have an operational significance. They appear as error exponents in many quantum information tasks. So now let me speak about some other problem, or which already appeared here in the previous talks, and it is the case of equality in this data processing inequality. So the question is, if you have a pair of quantum states and a channel such that this relative entropy is finite, so when does it happen that equality is achieved? So this condition was studied by Danish in 1986, and it was introduced as a quantum extension of classical sufficient statistics. So in classical statistics, this is a very well established subject. So if you have a pair of probability distributions and a statistic t, then we say it is sufficient with respect to this pair if the values of the statistics contain all the information which is needed to distinguish between these two distributions. And this can be mathematically expressed, for example, in the way that there is a common version of conditional expectation with respect to the statistic. But for extending to the quantum for quantum states, this is not a good definition because conditional expectation may not exist at all. So Danish looked at an equivalent characterization by Kublat-Leibler, which is given in terms of the classical relative entropy, also very similar equality. I will speak. Yes, so all these results I will speak about are true for normal states or for Neumann algebra. And here we assume that sigma is faithful, or at least we need that the support of rho is contained in the support of sigma. And we also assume that this relative entropy is finite. Then there are several equivalent characterizations of this equality. Perhaps the most important one is this, which you have already seen, which means that this equality appears if and only if there exists a channel which recovers both states rho and sigma. And in this case, we say that phi is sufficient with respect to rho sigma. So this term sufficient refers to classical sufficiency, but sometimes also the word reversible is fine. Okay, and this property can be seen as a definition of sufficient channel because it has a form of statistical isomorphism. Another way to characterize sufficient channels is to use different kind of divergences. So we can say that if we have a divergence which satisfies data processing inequality, we say that it characterizes sufficiency if this equality, in the case that it is finite, implies that phi must be sufficient with respect to the pair of states. And the following divergences have this property. So of course the relative entropy, as I already showed, and then it is the standard Renyi relative entropy with values in this interval. So for alpha equal to 1/2, it was proved already by Danish in 1988, but it can be very easily extended to all these intervals. And in finite dimensions, this property was proved for a large class of F divergences. Another important result is the existence of a universal recovery channel, or Petz recovery channel, which in finite dimensions has this form, but it was really defined in infinite dimensional context. Note that this channel always has the property that it recovers sigma, and theorem is that phi is sufficient with respect to this pair if and only if this channel recovers also rho, so it's really a universal recovery channel. And this channel is important in many applications. So another condition can be expressed in terms of conditional expectations. So note that by the last conditions, rho and of course also sigma must be invariant state of some special channel, which is the composition of these two, which implies that there must exist a conditional expectation which preserves sigma, with the property that phi is sufficient with respect to rho and sigma if and only if this conditional expectation also preserves rho. So in finite dimensions it can be shown that this has an impact on the structure of the states, which means that there is a sort of decomposition. So this U here is some unitary, and this sigma and L and sigma and R are some states, lambda and R probabilities, such that phi is sufficient with respect to rho and sigma if and only if rho has a corresponding decomposition. Here these sigmas are fixed, but mu's and that these states can be arbitrary. There is also a corresponding restriction on phi. It's not written here, but one can see that the range of the conditional expectation corresponds to this L part, and the adjoint of this channel, which is a unit LCP map, must be multiplicative on a subalgebra which is isomorphic with the range of E. So if this adjoint is not multiplicative, or the multiplicativity domain is trivial, then sufficiency means that these two states must commute. So this is a very strange, very strong condition. The applications of these results are found mostly in characterizing of equality in various entropic inequalities, most notably in the strong subadditivity of entropy. And this kind of decomposition of states was used to characterize quantum Markov property. And also monotonicity in various other quantities was studied using this decomposition. And as already the previous speakers mentioned, there has been a lot of study of the approximate version or recoverability, which means that there is a lower bound on this value, which is given by here some divergence measure. It's minus log of fidelity or measured relative entropy, and this phi tilde sigma is a modification of Petz's recovery channel, which recovers sigma and approximately recovers rho, and this inequality shows that this difference gives an upper bound on how precisely this rho can be recovered. Okay, so the topic of my talk is mostly concentrated on another version which appeared a few years ago. It's the sandwich Renyi relative entropy, and it was shown that it for some values of alpha, so this is also if rho and sigma commute, this is also a version of Renyi relative entropy, the classical one. And if alpha is in this interval, then it satisfies the data processing inequality and the other good properties. Also the limit value if alpha goes to 1 is the relative entropy, and an operational interpretation was found for alpha larger than 1 in quantum hypothesis testing. Okay. So for the rest of the talk, my purpose, so I have two things. So first is to extend the sandwich Renyi relative entropies to normal states of Feynman algebras and show their properties. So you may ask why do this extension, but regarding that the Danish's results are all in this framework, in this general framework. It's a natural question, and also not all problems in physics can be described in finite dimensions. So it's a natural question. And it was also proved that the standard versions have an operational interpretation in hypothesis testing, also in the von Neumann algebra framework. So this is also one of the important questions for the sandwich Renyi entropies. And the second aim is to, in this general setting, to prove that these versions of sandwich Renyi entropy characterize sufficiency for channels for these values of alpha. This is a question I was asked on the previous Beyond I.I.D workshop in Banff, so I think maybe it could be interesting still after 3 years to hear the result. Okay, so about the extensions of the sandwich Renyi entropies, there are two constructions for von Neumann algebra, or basically 1.5 construction, because this second one is only for the parameters larger than 1. And the use of non-commutative LP spaces is not surprising, because it was observed already in finite dimensions that such LP spaces play some role. The first construction is due to Berta Scholz and Thomas Michael, and uses Araki Masuda LP spaces. And the second construction uses Kosaki LP spaces. So to introduce, so I will speak about this this second construction, but it will turn out that these two are actually equal, so it's good. So to introduce Kosaki LP spaces, I need to speak about Hagerup LP spaces, which you already heard about in the previous talk. It's mostly because when we worked with a von Neumann algebra, we need a suitable representation, so-called standard form, and this will be used to have such a representation. I will not define the Hagerup LP spaces, so if you are not comfortable with this, then you can look at the case of an N is the algebra of bounded operators on some separable Hilbert space, and then we can replace Hagerup LP spaces by Schatten classes with the usual Schatten norm, so you can understand all what will follow in this setting. So some important properties of the Hagerup LP spaces is that for L infinity, M is isomorphic to the algebra. Then the predual or the space of normal linear functionals is isomorphic to L1M, and this isomorphism is given by this. So for this linear functional, the corresponding operator is defined as H rho, and this defines a sort of trace operation on L1M. And L2M is a Hilbert space with respect to this inner product. So on the standard form can now be introduced on this Hilbert space on L2M, where M is represented by left multiplication. I will not use this lambda, so I assume that it's represented in this way. Here we have also the positive cone, the distinguished positive cone in L2M, where any positive linear functional has a unique vector representative, which is given by the square root of the corresponding operator, and this means that it's a vector representative. Now I can define the Kosaki LP spaces with respect to a faithful normal state. So I assume now that sigma is faithful, and then we can define a continuous embedding of M into L1M just by this formula. So we have the usual Hölder inequality. So this implies that these are really elements in L1M, and this embedding is continuous. And if we take look at the range of this embedding, we can denote it by L infinity m sigma with norm defined in this way. One can observe that if we take a positive normal functional, then the corresponding operator is in this L infinity space, if and only if there is such majorization by sigma, where the corresponding norm is just the intimum of all lambda satisfying this majorization. And now we have this L infinity, m sigma and L1m as a compatible pair of Banach spaces, so we can construct the interpolation space, which will be denoted by LPM sigma, and the corresponding norm will be denoted by this. And fortunately, we can represent the elements in this space in this form. So if we take P and Q is the dual parameter, then LPM sigma is just the space of all elements in L1M of this form, where K is an element in the LPM, and the corresponding P sigma norm is just the P norm of K. So now we can define the sandwich Renyi entropy for alpha larger than 1. But to do it in general, we need to extend to non-faithful sigma, basically by restriction to the support of sigma. So we see that elements here have to have supports contained in the support of sigma, and then we just define the sandwich Renyi entropy in this way. So using the norm of H rho. If H rho is in this space, or it's infinite if it's not. Now, using standard methods of complex interpolation, we can prove a lot of properties of tilde d alpha. For example, strict positivity, lower semi-continuity of an extension to all positive normal functionals. Then we can show that this function, as a function of alpha, this is strictly increasing, and also some quasi-convexity and also other important properties. But I would like to speak a bit more about some properties like relation to the standard version and limit values. So for normal states, we can show this inequality for any alpha, and since we know that if alpha goes to 1, this goes to the usual relative entropy, and this also, so we obtain this limit value for the sandwich Renyi entropy. And if alpha goes to infinity, we obtain a natural version of relative max entropy. Now we can also prove data processing inequality, but here we don't take really a quantum channel, but it is enough to take a positive map between the L1 spaces, which preserves the trace functional. It can be seen that phi defines a contraction in these L1 spaces. And also we can show that it preserves the L infinity space simply by positivity. So if you have a positive element, then this inequality also implies this inequality under phi. So we have this map, and this extends since we know that the elements here have this form, then extends to a map x to y between the two algebras. Which map which are given by this equality, and this can be seen that this map is exactly the adjoint of the Petz recovery channel phi sigma I was talking about previously, and this definition is the definition given by Petz in 1984. So it was defined in this very general framework where even the sigma here was allowed to be a weight. So it's really yeah, something wild. Using this map, it can be shown that phi defines a contraction also for the L infinity spaces. And using a version of restoring theorem, we obtain that this phi defines a contraction for all p. And looking at the definition of the sandwiched relative entropies, we immediately obtain a data processing inequality with respect to positive trace-preserving maps. And this has a very important consequence. If we take the limit alpha goes to 1, we obtain a data processing inequality with respect to positive trace-preserving maps. This was first observed by Müller, Hermes, and Rieb in the case when M is the algebra of bounded operators. So this is sort of important because in all previous monotonicity results for entropy, there were some stronger positivity requirements for phi. So at least 2 positivity or some Schwarz inequality. Okay, so I want to say a few words about Araki-Masuda divergences. They were defined. The definition looks quite different from what I showed before. So this is some kind of generalization of Araki-Masuda LP norm defined by Berta Scholz and Thomas Mikkel. So these are some variation formulas. From these formulas, from these norms, one can obtain the definition of the Araki-Masuda divergence in this way. Here, note that differently from the previous definition, here we use the vector representation of the state row, and actually this can be defined using any star representation of M on a Hilbert space and any vector representation. This is somehow very useful. And there is a duality relation for usual duality between P and Q, and any vectors psi eta in this representing Hilbert space. And also for P between 1 and 2, we can find a unique unit vector such that equality is attained. This is somehow important. So to find the relation between these two definitions, we can observe that these LP norms can be also introduced by interpolation in a similar manner as before, but in sort of in 2 steps. So we first embed M into L2M and perform an interpolation, and then we embed L2 into L1M and then perform interpolation. And this is important in the final result, which shows that for alpha between 1 or alpha larger than 1, these two are actually equal. And we can also find for alpha larger than 1, so for these other values of alpha, we can find a convenient form. So if in this case this element here is in L2 alpha M space, and this d tilde alpha is just given by the 2 alpha norm of this element. And Berta Scholz and Thomas Mikkel also showed some limit values for alpha going to 1 and alpha going to 1/2. Now to prove the data processing inequality for d tilde alpha, we need to assume that phi is completely positive. So I don't know of any proof for positive or less than completely positive maps, because the proof needs a Stein-Spring representation. So I think I'm running slowly out of time, so I will be more quick. And the proof is based on the fact that we have some vector such that this equality holds. And here we use the fact that T is an isometry and duality of the norms. And since T eta is a vector representative of phi rho, and t eta 0 is a vector representative of phi omega, where omega is the vector state given by eta 0. Applying logarithm on this inequality, we obtain the following inequality. And here this alpha star is larger than 1, so from data processing inequality for these values we obtain the inequality here. Okay, so the last thing I would like to talk about is the theorem that the sandwich Renyi entropies characterize sufficiency for all values of alpha in this interval. So the proof can be found in these two papers. And just to remind you what it means, that such an equality, if this is finite, implies the existence of some channel which recovers the two states. So first I will going to show the proof in the case that alpha is larger than 1. Here this assumption implies that this corresponding element H rho is in the L alpha M sigma space, and so it has a finite norm, and phi is a contraction that preserves this norm. This already gives a very easy proof in the case alpha is equal to 2, because there L2 M sigma is a Hilbert space, and this Pet's recovery map phi sigma is the adjoint of phi. So by properties of contractions, Hilbert spaces, we immediately obtain this equality, so we have sufficiency, and we know that positivity of phi is enough here, so we don't need any complete positivity. Now for general alpha we can use interpolation techniques. So in interpolation we work with functions defined on some strip like this with values in L1M, and these functions are continuous and analytic on the interior, and we take a function of this form where t is some normal state or normal positive functional which with support contained in the support of sigma, and using the standard Hadamard three-line theorems, we obtain that if this equality, so that phi preserves the norm of such an element, if this holds for some alpha larger than 1, then it has to hold for all alphas. And so our assumptions imply that H rho has this form for some t and some alpha, and and we have this equality. So by the previous slide, this has to hold also for alpha equal to 2, so that we have sufficiency with respect to omega and sigma, where H omega has this form for we put alpha equal to 2, and as is some normalization constant. So this is not exactly what we wanted to prove, but some more work has to be done. And here we use the characterization of sufficiency by the structure of states. For simplicity, I will assume here that M is just a bounded operators on a Hilbert space, and we can replace H rho by the usual density operator of rho. In this case, we have this characterization of sufficiency, so we need to find the composition of rho in this way. But we know that we have such a decomposition for omega, because omega is sufficient, so phi is sufficient with respect to omega and sigma, and this implies decomposition of tau. And since rho has this form, we obtain decomposition for rho. So this implies the result. In the general case, we use conditional expectation and extensions of conditional expectation to Hagerup LP spaces and their properties. Now for the case alpha between 1/2 and 1, we know that this element is in the L2 alpha space, so we can use the polar decomposition. So there is some element here, some positive normal functional, and some partial isometry U. And we recall the inequality which was in one of the previous slides. And the equality condition means that these two inequalities are equalities, which means that this one here has to be equal to 0. Since here the alpha star is larger than 1, we have some sufficiency results. And actually we can show that this omega here has this form where tau is given here. So now we use similar reasoning as before, and use the composition or conditional expectations as before, and obtain the result. So this is actually all what I wanted to say. Only maybe I will mention some open questions. So, for example, we had this data processing inequality of relative entropy with respect to positive trace preserving maps. So it would be interesting for what kind of other divergences or F divergences it can be proved. Also, it was shown that for the case alpha equal to 2, we have this sufficiency characterization for positive maps. So it would be, yeah, it's also a natural question for how far we can go with this. And for example, we can look at these recoverability results and look at the possibility to extend them to this von Neumann algebra setting, and it seems that it can be done in a very similar manner using interpolation as it was in the finite dimensional case. So this is something which has to be done. So, but this is also. Thank you very much for your attention.
Are there approximate sufficiency conditions for Renyi entropies or Renyi relative entropies?
You mean approximate in this form of recoverability? Yes, as I said, not yet, but
even in the finite dimensional.
Okay, there are some for the case alpha is larger than 1. There are some lower bounds on these differences of entropies, or these increases, or this decrease of entropies, but they are actually proved in von Neumann algebraic setting, but it's not clear if they are of any use or if there is any interpretation. So
the lower bound is itself in terms of the same alpha.
It's in terms of a dual, so not alpha, but yeah, and it's in form of in terms of the A group LP norm. So not in a form of some divergence or of some relative entropy, but of some difference of two elements in this in some kind of A group LP norm.